A capacitor is an ideal basic circuit element. And the way to think about a capacitor is exactly the way that we've described it. It's two parallel plates separated that are connected up to wires. And it has some capacitance value C. And that capacitance value can vary depending upon the separation between the plates or the area of the plates for a parallel plate capacitor. Capacitors are useful because of what you've seen. They can store energy. That's a very useful thing for a circuit element to be able to do, is to store energy. And then you can release that energy at some point when it's convenient and useful. So that makes a capacitor a very useful basic circuit element. So we're going to start talking then about using capacitors as parts of a circuit. So let's talk with just capacitors solely by themselves initially. It turns out that capacitors can be combined to make different levels of capacitance. You can take one capacitor and combine it with another capacitor, and when you do that, you create a different level of capacitance. So here's one way to do it. Let's say that we've got 3 capacitors here that are hooked up end to end like that. Let's call this capacitor 1. It has capacitance 1, capacitance 2, capacitance 3. Now, those are connected up then to a battery. Now, the way to schematically draw a battery looks very similar to a capacitor, but it's not the same. You have to look carefully. It has one long plate and one short plate. That's a battery. And let's connect these up that way. So this is a battery, and that has some voltage across it. This could be like 12 volts or 10 volts or 5 volts or 1.5 or whatever. It's got some voltage. Now, the long line indicates that that's the high potential side of the battery, and the short line indicates that that's the low potential side of the battery. And if we connect these up, then there's going to be a current that's created that flows, appears to flow, through these capacitors by the mechanisms that we've already talked about. So we're going to have a positive charge build up on that one, followed by negative here, positive there, negative here, positive there, negative here, and it's going to continue on. So all of these appear to have the same current. They have the same current. And the charges that build up here, because they're all getting the same current flowing through them, the charges are going to all be the same on all of these. So they also have the same charge on each plate. Now, the total charge for each capacitor is still 0 because you have just as much positive as negative. So this Q here means the charge that's on one plate. It's the same for all of the capacitors here. All right. So those identify this type of connection with capacitors 1, 2, and 3 connected end to end like that as being connected in series. So these 3 capacitors are connected in series. Now, what does that mean? That means that they have the same current flowing through them. In fact, that's a general statement, not just for capacitors, but for every circuit element we will encounter. If it has the same current flowing through it as another element, then those elements are in series then. All right? Well, there is one other quantity we need to talk about, and that is the voltage, the potential of each capacitor. If you imagine that you have, let's say I have the probes. These are the probe ends of a digital multimeter that has the ability to measure voltage. And if I put my multimeter across this battery right here, it's going to read whatever the voltage of the battery is. Now, let me show you something. If I take the probe ends of my multimeter and I move them out here to the corners, I still, through these wires, have a direct connection back to the battery. Exactly back to the battery. So we assume that our wires, for all of our circuits that we'll encounter here, our wires have no resistance. They are perfect conductors. There's no energy loss. So I'm going to still measure whatever V is. And if I put it up here, now I'm still going to measure what V is. In fact, if I put the probe ends right here, I still measure whatever V is because I still have a connection right back to the battery. Now, if I were to do this, let's say that I keep one end on the left, but I put my other probe right there. What I'm going to measure is no longer going to be V. Instead, what I'm measuring is I am measuring the voltage across capacitor 1. Let's call that V1. And if I put them here, I'm measuring the voltage across capacitor 2. Let's call that V2. And if I put it here, I'm measuring the voltage across capacitor 3, and we'll call that V3. But remember, if I put it out here, I'm measuring the voltage for the entire system, which is just V. So what can we conclude from that? This voltage here, plus this voltage here, plus this voltage here, add up to be this voltage here. So what does that mean? The voltage is divided. The voltage V for the battery is divided across these three capacitors. And it's divided in such a way so that the total voltage V is equal to the voltage across capacitor 1 plus the voltage across capacitor 2 plus the voltage across capacitor 3. So we see that that's another general statement that happens to be true for these three capacitors when they're connected in series. So things that are connected in series have the same current, and things that are connected in series, their voltages add up to be the total voltage. Now, I could say that they also have the same charge, but that really only applies to capacitors. The capacitors are the elements that have charge on them. In general, though, for any element that's in series, it has the same current and the voltages add. Now, this is just one way to hook up capacitors, and we called that in series. There is at least one other way to connect up capacitors, and that is in parallel. When you connect things up in parallel, they don't have the same current, but they do have the same voltage. And let me show you that. Let's say that I have a capacitor here, then I connect to another capacitor here, and another capacitor here. So now these are my three capacitors, C1, C2, and C3. Now I'm going to take a wire and I'm going to connect them here and here, and I'm going to run that wire on down and connect it to a battery. So now here's my battery here. My battery has a potential of V. There. These are no longer connected in series, they are now connected in parallel. But let me convince you that this voltage is not the same down here. The voltages do not add for parallel. They add for series, but they do not add for parallel. And we'll convince you this way. Let's take the ends of my probe and let's put them across the battery. Well, what are they going to read there? They're going to read V, whatever V happens to be. And now I move them out here. What does it read? It still reads V. What about if I put them right here? Well, they still read V. Why? Because it still has a straight connection back to the battery. What if I put them here? Well, once again, there's still a straight connection back to the battery. There's a resistanceless connection back to the battery, so it still reads V. What about up here? Same. Still reads V. All right, well, what if I did this? What if I put my probe ends right there across capacitor 3? The answer is it still has a resistanceless connection back to the battery, so it still reads V. And if I put the probe ends here, still reads V for the same reason. Here, still reads V for the same reason. So what does that mean? That means all of these capacitors, the voltage across each one of them is the same. And what is that? That's just V. So the voltage total is the same as the voltage across capacitor 1, and that's the same as the voltage across capacitor 2, and that's the same as the voltage across capacitor 3. So the potentials, or voltages, across each of these is exactly the same. They all have the same voltage. All right, well, what does that mean for currents or for charges? Well, think about this. When we connect these up, the current is going to begin flowing out of the battery here, and we'll call that current I. But the current is a physical particle. Remember, we're talking about charges, which are real physical particles flowing through a conductor. So this flowing particle, when it gets to this junction right here, it cannot go both ways. It can only go to the right, or it can continue on up. Some of those particles are going to go this way, but some of them are going to go up here. And then when they get to this point, the same thing is going to happen. Some of them are going to go this way, and some of them are going to go that way. But whatever current goes up through here, through capacitor 1, let's call that current 1. That same current is going to come back on the other side. Remember, the capacitor has that type of current that makes it look like it's going in one side and coming out the other as it's charging up. So this current here is still I1. But when it comes down here, it's going to join up with this current that went through capacitor 2. Let's call that I2. So this is still I2 over here. So when those two currents come back through and join back together, they come out together. So this current here is really I2 plus I1. And then this current, which we'll call I3 going through capacitor 3, when it comes out the other side of capacitor 3, it's still I3, just like this one was still I2. And now they all three join back together and come back into the battery as I. So what does that mean? That means that if I is what's going in to these capacitors up here, but it's breaking apart into I1, I2, and I3, only to join back together to become I again, that means that the total I is really the sum of these individual currents. There's I1 plus I2 plus I3. So for the capacitors in parallel, the voltages are the same and the currents add. Whereas when we talked about series, the currents were the same and the voltages add. So that's a big difference between things being in series and things being in parallel. All right, well, what about the charges? Well, you remember the charge comes about because of the current that's flowing through it. So this is going to produce some charge on that plate and some other charge on the negative plate. The charges will be the same, but opposite polarities. But since the current is different, potentially different through each one of these, the charges are potentially different through each one of these. So this could have charge Q1 on it, Q3 on it. This will be Q2, and we'll say this is Q1 up here. So each one of those is a different current, and therefore produces a different amount of charge on each plate. Let me put it this way. If you took all of these capacitors here and you somehow combine them into one equivalent capacitor, let's call that CEQ. We're combining them together and we're making an equivalent system, but it only consists of one capacitor. The battery is exactly the same. Then the current that's flowing here would be the same I as this I. And that same I would go through the capacitor here back into the battery on this side, because we have a loop here and it's going to have one current. But the charge that's built up here, we'll just call that charge Q on that plate. Charge Q, whatever it is in this equivalent case, is equal to Q1 plus Q2 plus Q3. Now, why is that? That's because the currents are split. So the currents create individual charges. Remember the definition for current? Current is dq dt. So what does that mean? If we solve this for dq, that's equal to I dt. And then if you summed up all of the currents, this is all the individual dq's, I dt, like that, then what have you got? This is just the current over time, and this is the sum of all of the individual charges, and the individual charges is Q, is the sum of the current dt's. Now what does that tell you? I want you to recognize that there's a clear relationship here between the current and the charge. The current and the charge then are directly related. So if the currents add up this way, the charges will also add up the same way. All right? So the question becomes, how would you take all three of these and combine them into one like that? Well, that's the next topic here. Let's flip this over and see if we can talk about it right now. For that one equivalent capacitor, CEQ, it still obeys what is called the capacitance equation. What's the capacitance equation? Q equals C times V. Q was the charge on the equivalent capacitor, and V is the potential of the battery, which ends up being the potential across the plates of the capacitor as well. Remember down here, the potential here is going to be the potential across the capacitor there. Okay. Well, how do you know that? Well, once again, probe here, you get V. Probe here, you get V as well. But now it's the same as what's across the capacitor. It's just V. So that Q is Q1 plus Q2 plus Q3 for this case here, where we have the separate capacitors. All right? But that Q is also equal to this stuff up here, C equivalent times V. All right, what does that mean? Well, if I were to factor out the V here and say C equivalent is C1 plus C2 plus C3, then this Q1 is just, C1 times V1. Remember the capacitor equation. That applies to all capacitors. So for capacitor 1, back over here, Q1 is equal to C1 times V. The V is the same across all of them. So Q1 equals C1 V1, and Q2 equals C2 V2, and Q3 equals C3 V3. But remember, the V's are all the same. So those subscripts on the V's might as well not even be there because they're the same. All right, if that's the case, then this Q1 is C1V, plus this Q2 is C2V, and now Q3 is C3V, and all of that is equal to C equivalent times V. Now do what I did up here. Factor out the V. C1 plus C2 plus C3 equals C equivalent times V. And what do I have? The V's cancel. So the C equivalent is C1 plus C2 plus C3. So if you have capacitors in parallel, you combine them together to make an equivalent capacitance just by adding together the individual capacitances. So I could write this generically. C equivalent for any capacitors that are in parallel is equal to the sum of the individual capacitors from I equals 1 to n, where n is the number of capacitors that are in parallel. This only works for capacitors in parallel. If the capacitors are not in parallel, this doesn't work. If the capacitors are in series, then this doesn't apply, because in that case, we don't have these relationships here. Instead, if we want to combine capacitors in series, we have to use another technique. But for capacitors in parallel, remember this. It's just the straightforward sum of the individual capacitances. All right? Well, let's see what happens for capacitors in series now. Let's go back to our example where we have 3 capacitors that are in series. This will be C1, C2, C3 that are connected up to a battery like that, V. And remember, this is a high side, that's the low side of the battery. Well, this capacitor is going to have some voltage V1 across it. This will have some voltage V2 across it. This will have some voltage V3 across it. And the potentials, you know, add up. In other words, V equals V1 plus V2 plus V3, because these capacitors are connected in series, like that. Okay, well, the capacitance equation still applies for each capacitor individually. So what does that mean? V1 is equal to Q over C1, and V2 is equal to Q over C2, and V3 is equal to Q over C3. Now, why did I use the same Q's here? Well, because of what we talked about previously. The Q on this capacitor is the same for all of these capacitors. So if I take this bit of information here and I combine it with what's up here, then this equation becomes V equals V1, which is Q over C1, plus Q over C2, plus Q over C3. Then if I factor out the Q, I have Q multiplied by 1 over C1 plus 1 over C2 plus 1 over C3. Then I can solve this and put it in the form of the capacitance equation. What do I mean by the capacitance equation? Q is equal to C times V. That applies for all capacitors. So if I took all of these capacitors here and I made one capacitor out of them that is the equivalent, C equivalent of all of those up there, this is still that, then in that case, whatever the charge is here, Q, is going to equal C times V, where this is C equivalent. That Q, by the way, is the same as each Q up here. They're all the same. They all have the same charge. All right? So if I try to put this equation in this form and I solve it for Q, what do I have? Well, it's all of that right there. I have to divide by all that. So it's 1 over C1 plus 1 over C2 plus 1 over C3, all of that, times V. So the equivalent here, you can see C equivalent is the same thing as all of that 1 over C1 plus 1 over C2 plus 1 over C3. Now I can simplify that a little bit by writing it this way. Let's take the reciprocal of both sides. So this is 1 over C equivalent is just 1 over C1 plus 1 over C2 plus 1 over C3. In general then, 1 over C equivalent is equal to the sum of all of the individual 1 over from I is equal to 1 to ever how many capacitors there are. And this is for capacitors in series. All right, so that would be how you combine capacitors in series, which is different than how you combine capacitors that are in parallel. Now let's work a problem so that you can see how all of this is put together into hopefully some coherent thoughts. Let's first of all combine some capacitors. Let's say that I have a system that is set up this way. Here. So these are the terminals. I would hook a battery up there, one terminal there, one terminal here. So this is capacitor 1, this is capacitor 2, and this is capacitor 3. All right, we'll give some numeric values here. We'll say C1 is 12 microfarad. We'll say C2 is 5.30 microfarad. C3 we'll say is 4.50 microfarad. And here's what we want to do. We want to figure out what is C equivalent for this situation here. One of the first things that you need to be able to recognize is which of these capacitors are in series and which of them are in parallel. Now remember, things that are in parallel will have the same voltages, but things that are in series will have the same currents. So if you want to determine if something has the same current, then imagine a current flowing through this. A current flowing through here, when it gets to that point right there, it has to either go to the left or to the right. So the current is split at that point. What that means is that this thing over here or this thing over here does not have the same current as C3. So that means that the C1 and C3 are not in series. C1 and C3 are not in series. But C2 and C3 are also not in series. So there is nothing here that is really in series. However, if you think about the voltages here, if I have my voltmeter again, and I put it across C1 and I measure that voltage, and then I put it across C2 and measure that voltage, these two things right here would have the same voltage. So these two things are in parallel. That means that you could take those two and you could combine them together into one equivalent capacitor. And when you do that, this system becomes this. This is now the equivalent capacitance that is C1 and C2 combined, and C3 is still down here on bottom. So let's call this C12. Now, what is C12? Well, C12 is just C1 plus C2. Because they are in parallel with each other, it's just a straight combination of those. Okay, but now we've changed the configuration a little bit. So now these, if you'll imagine a current flowing either up or down through these, the same current that goes through this one is going to go through that one because there's only one path for the current to go on. So these are in series now. So C12 and C3 are now in series. And if that's true, we can take all of those and combine them into one capacitor. And that one capacitor, we could call that C123, like that. That one capacitor is going to be given to us as 1 over C123 is equal to 1 over C12 plus 1 over C3. We could solve for C123 out of that. C123 is just C12 times C3 over C12 plus C3. Now, anytime you're combining two capacitors like this using this 1 over relationship here, you can think of that as just the product over the sum. Because if you solve for C123, that's what you get. You get product product divided by sum. That'll be a real handy thing for you to remember. That way you don't have to worry about the algebra to do all of this. Okay, so I can see that to combine all of these together, I need to do that. But in order to do that, I need to do this first. So now that I know the approach, I can figure out what the answer is going to be. Now I'm going to leave it up to you to do this, but I will tell you that C1, 2, 3 turns out to be 3.57 microfarad. If you do that and you don't end up with 3.57 microfarad, then you've done something wrong. I'm 99.9% confident in that answer right there. I would say 100, but scientists never say they're 100% confident. But that's the answer for this problem, I'll tell you that. So if you don't get that as your answer, then see where your error is and try to figure it out. We will pause here and stop and pick up with something similar next time.